Hello and welcome. Today we're going to be talking about areas between curves. All right, so this is actually a new chapter for us. We're now on to chapter 6. Okay, and this chapter is really all about, doing things with integration. All right, so we're going to be doing a lot of applications, basically, of integration. And in doing so, we're going to really learn how to build integrals that do specific jobs, or maybe you achieve some goal. Okay, so for now, we're going to start with kind of the simplest example, which is something we've been doing for a while, which is areas under curves. But traditionally, we always think of, having some function like this, and we find the area under the curve like that. So now what we want to do is now kind of generalize this. So we know, of course, that this is going to be the integral of a to b of f of x dx, if that's f of x. So what we want to do now is, instead of just doing that kind of basic thing, is to kind of just make it a little bit more complex. Try to build curves and shapes and areas that are out of more than just one function. So I'm going to start with a simple example. Let's look at the function y is equal to x squared. We're going to also look at the function y is equal to square root of x. All right, let's plot those two. Of course, square root of x kind of goes like that. And in fact, there's a parabola. This is actually the parabola x is equal to y squared, right? We could also write that, of course, as y is equal to the square root of x plus or minus, right? Okay. But if I just look at that curve, y is equal to the square root of x right there, right, that looks good. And we know here at 1, we're going to be at 1 there. Likewise, and I'll do this maybe, well, I'll do it in a different color. I'm going to do it in green. That is going to be, of course, y is equal to x squared. All right. So the goal here is to find the area between the two curves. Okay, and what we can see then, of course, is that I can draw that area where the two curves intersect and pinch off to each other. We have that little area there. So I want to know, what is that area? So that area actually turns out to be pretty straightforward to do. What we really do actually is we find the area under this curve. So we can talk about that as the area from 0 to 1 of square root of x dx, right? And then we also find the area under y equals x squared. If I take away that other area, like that, I will get the area between the curves. All right. So that's cool. But we might want to formalize this. In general, we can actually write it this way. It's the integral from 0 to 1 of square root of x minus x squared dx. We can put them all in one integral just to make a more compact expression, expressing that area right here. All right. Just for fun, we should maybe just go ahead and calculate that area. So that, of course, is going to be x to the 1/2 plus 1 over 1/2 plus 1 minus x cubed over 3. And then, of course, we're going to evaluate it at 0 and 1. All right, so that becomes a 2/3 x to the 3/2 minus 1/3 x to the third, 0 and 1. And then we get 2/3 minus 1/3 is equal to 1/3. Okay, so the area between those two curves is that. All right, so in general, we build an integral if I have, function f of x here, and I have some function g of x here, and if I have some a and b, like that, if I want to find the area between these two curves, the general formula, of course, is going to be the integral from a to b of f of x minus g of x. Okay, so I think that's pretty straightforward. But now we can see it might get more and more complicated, and let me just give you another example of this. Let's talk about this example here. Consider the area enclosed by the two curves y is equal to the square root of 2x plus 6, and the line y is equal to x minus 1. All right, so this is going to take a little bit of work to kind of, so we say it's the area enclosed, so it's going to be a little bit like last time. So last time, of course, we had those two areas, and there was these natural intersection points that allowed you to find that little pinched off little bit of area that we want to find. So let's see if we can find the area enclosed by these two curves. All right, so we know this line here, so why don't we draw that one out first? And we know that is going to be, it's going to cross the x-axis at 1 there. And it's going to go up like that on a diagonal line. It'll intersect there at -1 as well and go down. Right. For this other curve, though, we might try to think of another way to look at it. Let's see if we can actually take y and square it, and that gives me a 2x plus 6. And see if we can then now say that this is actually going to be y squared minus 6 over 2, and that's going to be equal to x, or 1/2 y squared minus 3 is equal to x. So if I were to draw that on the x going vertical and the y going that way, of course, this is going to be that's going to be a parabola. Right, in fact, it's a parabola that when y is equal to 0, we go 1, 2, 3, it goes down to -3 right there. Right, and then where is it going to, and it's going to intersect the y-axis at square root of 6 and the square root of 6, negative square root of 6, like that. All right, so when we flip that around, it's going to be, and I'll keep this. Remember, we're going to now flip these axes here, because we know when we're looking at our main plot here, x and y, what we really have to do is think about it this way and go 1, 2, 3, back to -3, which is where this is going to be x is equal to -3. And we know that the curve is going to go up like that, and it's going to go like this. And it should intersect at 2 points. And let's see if we can find those 2 points. What we really have to do, of course, is actually just set y equal and see if we can find the y values together. Or actually, it might be better to actually use this representation here in terms of x. I can actually plug that in. So what I can do is take y is equal to x minus 1, but now I'm going to plug in 1/2 y squared minus 3 equal to x into there and see if I can find the points of intersection. Okay, so that's going to be y is equal to a 1/2 y squared minus 3 minus 1. It might be a good idea to, we'll just keep simplifying. Right, I might want to do is multiply this whole thing by 2. And then what I'm going to get here, of course, is y squared minus 2y minus 8 is equal to 0. Okay, so with this quadratic, I think I should be able to solve this quadratic pretty straightforwardly. Okay, y is going to be equal to 2 plus or minus the square root of 4 minus 4 times negative 8. So you get positive there all over 2. Okay, so that should turn out that this is going to be equal to 4 and negative 2. Okay, you can trust me on that. We can do all the calculations, but we can probably just shortcut to that. Okay, and so let's find out where that y value then is going to be. It'll be somewhere. I mean, I don't need to draw it exactly, but it'll be somewhere down here. And that'll be negative 2. Okay, y is equal to negative 2. And we'll have another one that's going to intersect up here at y is equal to 4. All right, so now we have this nice looking shape. We do need to then actually plug in, if these are the two y values, let's actually find the x value. Well, the x value we can get a lot of different ways, but I think the easiest way, of course, is to plug it into the line equation. So 4 is equal to x minus 1. X is going to be equal to 5. So that's going to be here, x is equal to 5 up here. Likewise, if I take negative 2 is equal to x minus 1, we get x being equal to negative 1. So I didn't quite draw the curve about, maybe I need to draw it more like about right there. Yeah, that looks better. Okay. Okay. So that point there, of course, is going to be negative 1, negative 2. And the point up here is going to be 5, 4. All right, so we want to compute the area I want to figure out what the area is between these two curves. Right, the problem, of course, is, if we look at this, the problem is here, of course, is that we can't use the simple formula for area because we need to have the two curves be one be above and one be below. But in this particular case, there's no, one of the curves is kind of level with the other curve for the entire time. We can't necessarily, in fact, we can cut it off there. In fact, we could do it for a little bit. We can get this one wedge of it, but then we'd still be stuck with this piece right there. Okay, so it turns out it's better to look at this this function, or this thing, is actually to integrate in the y variable. So what I mean by that is actually we're going to take this to be the top curve, and I'll put a green line there. That'll be the top curve, and this will be the bottom curve there, right here. And we're going to integrate across here. We're going to integrate up, right? And what we mean by the y variable is we're going to integrate as a dy, all right? So how we're going to do it, we're going to start at, of course, -2, and we're going to go all the way up to 4. We just have to figure out what goes in there times dy. Okay, well, I think this one should be fairly straightforward. I'm going to go to the next page now. And recall then, of course, that we really have a y is equal to the square root of 2x plus 6. And then we also have the function y is equal to x minus 1. But now we need to express this as a we need to think about essentially flipping this thing over, right? So we need actually those other functions. Let me go back and get them. It's going to be x is equal to 1/2 y squared minus 3, right? Yeah. And now we can get this here to be y, or x, is equal to y plus 1. Okay. And really what we're taking here is we're going to take x to be the measure of width of the rectangle. Width of the rectangle, and then delta y will be that height of the rectangle. So this is a new interpretation. Let's draw our picture again. I'll just draw it very approximately here. And we had the point -1, -2. And we have this point up here, 5, 4. And there was our graph, like that. Okay, so what we're going to do now is we're going to break up our y axis into little partitions, and we're going to make little rectangles, like so. That are on, now these are horizontal rectangles. Oops, we need to keep moving them out. Sorry, I didn't bring them out like that. So there's all our rectangles there. And then our area is we're going to sum from I is going to go from 1 to n, right? And now what we're going to have is basically an x of yi star times delta yi, okay? Where x is going to be that. Actually, let's take that x and be a little bit more careful about it. We're actually going to call it a function of the width. So the width, though, will be a function of y, and we can think of it this way, is this function here, well, that's written by this line there, so that's on the right-hand side of things, right? This is the right limit, And then on this side, this is the left limit. Okay, what we can also say is basically that x left is going to be equal to 1/2 y squared minus 3, and that x right is going to be equal to y plus 1. All right, so it should be that the width function as a function of y is going to be x right minus x left. Or that should give me the width of each rectangle. All right, well, it's worth doing, so that's just going to be y plus 1 minus 1/2 y squared plus 3. All right, so that's my width function. All right, and of course, I'm now, instead of integrating left to right, I'm actually integrating from bottom to top. I'm actually integrating this way, and I start at -2 and I go up to +4. Okay, so with all of this, I should actually be able to put together an integral. I'm going to change colors now. I'm going to construct my integral. It's going to start at -2 and go to +4, and that width function, I think it's going to be pretty clear. It's going to be y plus 4 minus 1/2 y squared. That's a simple way to express it. dy. Okay, so that will be equal to the area. All right, so now it's just a simple matter of computing this area. So I have a y squared over 2 plus 4x minus 1/2 y cubed over 3, and we're evaluating it at -2 all the way up to 4. All right. Once we do all the arithmetic, it turns out we're going to get a 18 out of it. Okay, I don't think we need to go through any more arithmetic, but I think if you just evaluate that expression, you can get it. All right, so I think I'll stop here and say, okay, now we've got this idea that we can build these areas in this really neat way by just constructing an integral now to do a specific job. So we just had to work with the geometry and figure out the best way to build out those sort of sum of rectangles and then construct the integral appropriately, right? And that's going to take, again, some engineering is certainly involved in this. And of course, in all of Chapter 6, we're going to see many, many more examples of this type of thinking. There's going to be a lot of drawings, a lot of kind of figuring of how to figure out how to set this thing up to work the best. Anyway, I will leave it at that, and I'll see you in the next video.